All right, welcome back. So today we'll be looking at chapter 24. This is kind of summary chapter for the previous couple of chapters. Okay, so basically summarize what we learned in electricity and magnetism. So let's jump in here. So it was in the 19th century that James Maxwell um, he developed a theory that explained the relationship between electricity and magnetism and predict that visible light is also an electromagnetic wave. Okay, so we'll take a quick look on the equations that he developed. So he actually developed those differential equations, which will not go into detail, but those actually describe the relationship between electricity and magnetism. Okay, and also light is electromagnetic wave. So that's why on this shirt, some people say when God created light, he did not say that there be light, but he says those four differential equations and then light appeared. Okay, but um, those four equations, let's take a look just what they mean. Okay, so the first equation actually describe the electric field lines. So they are originate from positive charge and terminate on negative charges. So that's what we learned a couple of chapters back. Second equation describe the magnetic field lines, which they are actually continuous. So this is different than the electric field lines. So electric field lines do have a starting point and an ending point, but magnetic field lines they do not. They are closed. They are closed loops. Okay. The third equation basically says then if you have a changing magnetic field, then you actually create an electric field. Okay, and then the fourth equation says vice versa. If you have a changing electric field, then you actually have you actually produce a magnetic field in the region surrounding it. Okay, so that's what we need to know about those. Since light is also a type of electromagnetic wave, and according to those four differential equations, the Maxwell's equations, all electromagnetic wave travel at the same speed in vacuum. So the electromagnetic wave travel at the speed of light. Okay, according to those equations, you can derive that speed of light is determined by those two constant numbers that we have seen recently. So mu naught and epsilon naught. Okay, so mu naught is 8.85 times 10 to the minus 12. Epsilon naught is 4 pi, or the other way around. Epsilon naught is 8.85 times 10 to the minus 12, but mu naught is equal to 4 pi times 10 to the minus 7. Okay, so take those two constant numbers in here, you get speed of light close to 300 million meters per second. Okay. So that's the speed of light. That's also the speed of electromagnetic wave, which we'll call EM waves um, here afterward in vacuum. And it was proven or kind of observed by Hertz that the generation or detection of EM wave. So you actually basically have RLC circuits in the AC powered by an AC source, and then over here there's a transformer. So those are that's the sign for transformers in this coil, and there's kind of this spark gaps here. So this is the type of RLC circuit over here because this is a AC power source. So then you actually generate AC signal here at these 2 points. So sometimes you would have a positive on this side and a negative on this side. So you actually generate an electric field here that is alternating. So sometimes the top here is positive. Sometimes the bottom top is positive, okay, and then vice versa. So since you have a varying electric field, then you have a magnetic field, varying magnetic field produced, and varying magnetic field actually will produce varying electric field. So you have an EMF wave, and then it can be detected by another loop here, okay? And then we'll see that later on. These are called antennas, okay? So, but then signal can be going through a tuner, which will be similar like this guy, and then amplifier, etc. In the um, electronics, okay? So for example, if you have an AC radio or AM radio or FM radio in that sense. All right, so let's take a look at the production of electromagnetic wave closely. So as I mentioned in the previous slide, if you have a gap and then that is connected to the AC signal, so it's similar to here, sometimes you have positive and negative here. One way of doing this is if you have charges, um, you can actually make the separation of the charges vary. So sometimes closer to each other, sometimes further away from each other in that case. So then the electric field produced by these two charges is then actually vary, okay? Because electric field also varies as the distance you are away from the source charges. So once you have varying electric field, then you can generate magnetic field here in the blue either dots or cross. Okay, so on the two side of the this piece of the block, it's going to be magnetic field is going to be pointing into opposite directions. Okay, and so this is when you do that, when you do varying the two the separation of the charges. Okay, so then you have varying magnetic electric field, which produce varying magnetic field. Now, one thing to keep in mind or take note is that electric field, if you have electric field in the plane of the paper, then magnetic field produced will be perpendicular to the plane of paper, okay? Because you can imagine this is kind of like current and then B field, okay, in that sense. Now, once you have this magnetic field generate, because it's due to varying electric field, so then the magnetic field actually is also varying. Okay, so you have to actually have a varying magnetic field in that case. Now, varying magnetic field will further produce a new varying electric field. Okay, and then on if you are doing in sun scenario over here, when you have the separation the largest, okay, and then you have also this is kind of, so it produced a varying magnetic field, electric field and magnetic field, and then varying magnetic field produce varying electric field, and then varying electric field further produce magnetic field, okay? Magnetic field, varying magnetic field further produce an varying electric field. So in that case, then the EMF wave are just propagating outward, okay? So this is similar to just a mechanical wave. If you have water wave, so it will propagate outward as the same, okay? All right. This is will be then similar to or exactly the what we had in the previous case a couple of slides ago. So so it'll be this one here. So you have spark gap over here, and then this is pretty much AC signal over there. Okay, so it's kind of like that. And then you're generating varying electric field, okay, as the signal varies. Okay, so sometimes you get zero, sometimes you get flip the sign of the voltage, which means you flip sign of the electric field. So you produce a varying electric field, and then the varying electric field produce then the varying magnetic field, and magnetic field, varying magnetic field further will produce a new set of electric field propagating outward. Okay. So electric field will be varying, magnetic field also will be varying in the EMF wave, okay? And they are perpendicular to each other. So if electric field is in the J direction, magnetic field then is in the Z direction. The propagation of the EMF waves then is perpendicular to both the electric field and magnetic field. So that means it's going to be in the X direction, okay, in that case. And according to Maxwell equation, so this relationship is always true. Electric field is equal to the speed of light, which is called c, times the magnetic field. Okay, so in that sense, you can see just looking at the number, the magnetic wise electric field is greater than the magnetic field by the speed of light. Okay, so a couple things to remember here. Electric field and magnetic field are perpendicular to each other in EMF waves, and the propagation of the wave is then perpendicular to both of these. And then at all times, electric field is equal to speed of light times the magnetic field. You guys probably have seen this electromagnetic wave spectrum somewhere. So EMF wave actually could be very long wave having long wavelengths, okay? Or it could have very short wavelengths. So depending on their wavelengths, they can be categorized as different waves. So radio wave, AM wave here, TV signal, FM wave, microwave there, infrared EMF wave, and then there's this small band over here, which is the visible light. Okay, ultraviolet, X-ray, and gamma ray, etc. So that small band, if you zoom in, you'll see different colors in that small light band. Okay, visible light band. All right. Next, we'll take a look on the energy in the EMF wave. So electric field, because there's electric field and there's magnetic field inside the EMF wave. So then there will be energy inside the wave. Okay. Now, energy density, if we remember, energy density is actually proportional to the field square, E square or B square. So then if magnitude of electric field or magnetic field doubles, then the energy actually will quadruple. Okay. So in that sense. All right. So the energy in the end. So a quick recap of what we learned when you have electric field. So energy is then density is proportional to E square, 1/2 epsilon naught E square. In the magnetic field, energy density is 1/2 mu naught, but also B square. Okay. So then total energy in the EMF wave then will be combination of these two. Okay. So UE or mu E plus mu, oh yes, lowercase u should pronounce as lowercase u here. That means energy density should be these two combined. Okay. So this one plus that one. And because electromagnetic wave is a sine function, the E field is a sine function or cosine function. Also, B field is a sine function or cosine function. So then the average energy density would be 1/2 epsilon naught. We can use RMS quantity of electric field score, and then also for the B field we use RMS magnitude of B and then squared. Okay. And because E equal to C times B, so then we can use that relationship that either just write B as E over C or E equal to C over B. So then this combination can be either becoming epsilon naught E RMS square or 1/mu naught B RMS square. Okay, so you can actually derive this relationship yourself outside of the class. And so either just purely you can express in the form of RMS quantity of electric field or the RMS quantity of B field. All right. Next, we'll take a look at the term called energy density. So energy density is the energy delete over a certain area in the given time, unit time. Okay, so delta U over A times delta T will be actually equal to the energy density. And delta U, that's total energy. So let's say this light, this EMF travel delta T. So then it's the total energy of this volume of the light. Okay, so volume times energy density will be there, divided by area times delta T. So A cancel, delta T cancel. So then it just gives you energy density times the speed of light. Okay, so intensity can be that, or if we look at the delta U over delta T, that actually gives you power. So it can also be power over area. Okay, so either of these expression, these two expression will give you your energy density or energy intensity. Excuse me for that. All right. So intensity then it's UC. U will be 1/2 epsilon 0 E squared and then times C plus the second term 1/2 over 2 mu naught B squared, but also times C. Okay. And then again, you can just use the equation of E equal to C times B. So then it can be purely just in terms of electric field times the constant numbers, constants, or just the B field time times the constants or divide by the constant. Okay. All right. So the average then can be again either just use the E field. Okay. So this is for the and if we are using the maximum, not the RMS. Okay. So when you are using RMS, you don't have the on half here. But when you use the maximum, the peak value of E field, okay, then we do divide by 2 because this is E peak score over 2 will be equal to ERMS score, okay? The same thing for if you just want to express in terms of B maximum score. So then there's a factor 2 there as well, okay? All right. We'll take a look at this example here. So this one says lasers can be constructed to put that can be constructed that produce a extremely high intensity EMF wave for a brief time called pulsed lasers. They are used to ignite nuclear fusion. For example, such a laser may produce an electromagnetic wave with a maximum electric field strength of 1.00 times 10 to the 11 volts per meter for a time of just 1.00 nanoseconds. What's the maximum magnetic field strength in the wave? And then B, what's the intensity of the beam? What energy does it deliver to this certain area? Okay, so let's take a look here. So we are given this is electric field. Okay, so this is E field. This guy is the E field, and then this is the time delta T, and then this is the area. Okay, so those different numbers. We are looking for maximum magnetic field. Okay, so remember magnetic field and E field have a relationship of E equals to C times B. So then for B max, okay, so let's call it B naught, should be E naught over C. Okay, so this one will be kind of straightforward here. Over C, we will just use 3.0 10 to the 8th, okay, meters per second. And if we use everything in SI unit, our result should also be in SI unit. So this will be 3.3 10 to the second, and B field should be in the SI unit of Tesla. Okay, so that's on that one. B, what's the intensity of the beam? Okay, so intensity of the beam. So it's I. We can use so there's a few expressions you can look up in the slide. So because we are given electric field, the maximum, so then we can use this E. This guy will be, if we are using maximum, then it will be 1/2. Okay, so 1/2 of C, speed of light, epsilon naught, and E naught score. Okay, so if you given RMS, then there's no 1/2. Okay, so again, we should just plug in the numbers we know. For speed of light, 10 to the 3 times 10 to the 8th. And then if you're given this as 1.0 10 to the 11th, and let's score, okay? So all this come together, that gives you, I think I'm forgetting epsilon naught. Okay, so epsilon naught is somewhere, should come in here after the C, that's 8.85 10 to the minus 12 F over M farad over meter. Okay, so if you put that somewhere there, and then this gives you 1.33 10 to the 9th watts per meter square. Okay, because intensity could also be power over area, so units will be watts per meter square. All right, the last one says what will be the energy delivered to that area. Okay, so we have intensity, so the energy U will be intensity times delta T times area, okay? Because intensity defined as energy over a certain area under time t, delta t, okay? So then looking for U, you should multiply A times delta T to both sides of the equation, okay? So then we'll just use the those numbers, 1.33 times 10 to the ninth. All right, and then actually 19th. Sorry about that. So previously that's 10 to the 19th, okay? Watts per meter square. And area, we can do area first and then delta T, or either way, doesn't matter. So area is 1.00 millimeter square. So that means 10 to the minus 3 meters. That should be squared. Okay, so because millimeter is to be squared. Okay, and then times area. Oh, actually, we did area. So times the time. So this pulse laser is 1 nanometer. Okay, so it's 10 to the minus 9 or 1 nanosecond, 10 to the minus 9 seconds. Okay, so this gives you totally 13.3 times 10 to the third joules, which we call it kilojoules. So 13.3 kilojoules. Okay, on that. All right. So going back to this slide there. So there's a link here. You guys can click on your lecture notes. So it's basically also a quick review of electromagnetic wave, but I figure might be will be helpful if you listen to someone else explain the electromagnetic wave. Okay. So watch that, and then hopefully you'll pick up a thing or two from there as well. All right, so we'll stop here today, and then we'll come back another time. Okay? See you guys.